Hello everyone, my name is Michiel Dhont, and together with some colleagues of the Elucidata Lab of series, I did some research about the layered integration approach for multi-view analysis of temporal data. So let's start with the rationale. So first of all, industrial assets can generate a lot of data which contains a lot of information. So if we would mine this data, this allows to derive relevant insights in general. However, there are some challenges related to these kind of real-world data sets. First of all, they can consist out of multiple heterogeneous subset of parameters. An example in here can be that there are operational measurements, so this can be the measurements which control the status of the system. But another group of parameters can then be the exogenous factors. So this can be factors about the weather temperature, for example, the surroundings around the asset. A second challenge related to real-world datasets is that there are often different sources. So this is good because more sources means there's more data available. However, each dataset can have parameters which may differ in resolution, in data quality, in technical configuration, etc. So it's quite hard to keep all the information which is in it, because so the most easiest solution to use data from different sources might be to pool these data sets together, but yeah, this can result in information loss and masking of source specific features. So we need to find a more intelligent way to handle this kind of data. We will illustrate our novel approach based on a case study. For this, we will use SCADA data from a fleet of 4 wind turbines. So SCADA data means supervisory control and data acquisition. So in here we have per wind turbine 31 sensors at a 10-minute time interval. So and this for a time range from 2009 until 2017. So and here we have multiple heterogeneous sources. So first of all, we have the endogenous source sensor, so like the pitch angel, the torque, and the gearbox oil temperature. Another heterogeneous subset is the exogenous sensors, like the wind speed, the wind direction, and the outdoor temperature. And then last but not least, of course, in a wind turbine case, is the output sensor, so the active power and the reactive power, and some other similar measures. And so these are located in La Haute-Borne in France, and they are from the company of Engie. The goal in this case study is to identify time windows where a wind turbine is having a consistent behavior, and we will do this by exploiting the heterogeneous views from the whole fleet. So the novelty which we want to show you in this presentation is actually our layered integration approach. So with this approach, we want to exploit both the multi-view and the multi-source nature of data, which is often present in data. And it should be agnostic to the specific mining technique which is selected. So we can use it for clustering, as we will illustrate in our use case, but we can also use it for regression, classification, etc. As you can see in this illustration here, our layered integration approach works with 3 layers. So first of all, there is the individual analysis, then there is the mediation analysis, and last there is the integration analysis. But how this works will we now explain step by step. So let us start with the first layer. This layer we called the individual analysis layer. In here we consider only a subset of parameters, and this subset should facilitate the identification of the characteristic behavior within each individual source. In our wind turbine use case, this can be the operational parameters like the pitch angel, the rotor stator temperature, and the torque. Then with this data, we will perform an individual analysis per source. In our use case again, this is like clustering the timestamps per wind turbine. And as an output, then we have one data model per source. In our case, this will be clusters, which represent the distinctive operating modes per turbine. Like an operating mode is what we call one typical behavior at a typical time for a wind turbine. So once we have these source-specific data models, we can go on to the second layer. This layer we call the mediation analysis. So in here we use an alternative subset of parameters which are able to facilitate the comparison and the mediation across the different sources. So in our wind turbine case, this can be the exogenous parameters like the wind speed, the wind direction, the outside temperature, and so on. So we will use this data to transform the results from the first layer in an alternative representation. In our case, we used performance profiles for the wind turbine, but what this exactly means will be shown in another slide. So as outputs, we get some data model representations which are comparable across the different sources. This, in our use case, this is the probabilistic profiles of the expected production of performance in a turbine. So now we can go to the third layer. We call this layer also the integration analysis layer. So in the first and the second layer, we only did some analysis based on source-specific turbines. So we didn't fuse anything together from different sources. However, in this step, we perform a cross-source analysis based on the results of the mediation analysis, so the results of the second layer. In our wind turbine case, this means that we will cluster the turbine-specific operating modes by these performance profiles into fleet-wide operating modes. So based on this, we can do some integration and trace back similar cross-source performance to certain characteristic behavior of the individual sources. For example, in the wind turbines, this can be that we can identify fleet-wide operating modes which are potentially responsible for a certain production performance. So the output in here is like an explicit link between the data models resulting in the previous two levels. In the wind turbine case, we get a unique link between the production performance profiles of the fleet and the characterized operating modes. Now I will show you the results which we obtained with our wind turbine use case. So we have a fleet of 4 wind turbines. Then in the individual analysis we did per wind turbine, we extracted distinctive operating modes per turbine. So we clustered the timestamps based on a subset of the parameters. And then here you can see for one of the wind turbines the torque curve for each operating mode. So as you can see, based on only those 2 parameters, we can already see some difference between all the operating modes. In the mediation analysis then, we used a different subset of parameters, so the exogenous parameters. And based on the exogenous parameters, we multidimensional bins each operating modes, or the points within each operating modes. And then for each bin, we extracted an individual probability distribution. So you can see for one of these operating modes, we get a lot of these distributions. Then we did some filtering on this, so if we don't have enough points within a bin, then we remove this. And then we obtained one weighted mixture probability distribution per source-specific operating modes, which we then can exploit in the third layer to extract the fleet-wide operating mode. So we clustered all these expected production profiles together into operating modes, which resulted into 4 operating modes. And as you can see, each wind turbine has multiple similar operating modes. For the conclusion, we have proposed a novel generalized multi-view data analysis approach for heterogeneous real-world datasets which are originating from multiple sources. And we demonstrated this on a real-world dataset of a fleet of wind turbines. Thank you for staying with me during this presentation. If there are some questions, don't hesitate to contact me by my email, or you can also find the paper by the QR link on the screen. Thanks.